1, 4. Here's our diagram. There's the point A, 3, 1. There's the point B, which is minus 1, 4. Then we might want to find the equation of the line that passes through them. Now, in high school, you may have learned that in order to solve this, you need to solve some little system of two linear equations. This is giving you an alternate and very powerful way of solving this important problem. What we do is we convert the points into projective points. So 3, 1 becomes 3 to 1 to 1, and minus 1, 4 becomes minus 1 to 4 to 1. And then we just apply this formula to write down immediately the projective equation of the line passing through those 2 points, which is what? Okay, so the first entry is obtained by looking at the second and third entries here. So it's 1 times 1 minus 1 times 4. The second entry is obtained by looking at the first and third entries here and here. It's 1 times minus 1 minus 3 times 1. And the third entry is obtained by looking at the first 2 entries here. It's 3 times 4 minus 1 times minus 1. And that amounts to 1 minus 4 is minus 3. Minus 1 minus 3 is minus 4. And 12 minus 1, 12 plus 1 is 13. So we end up with minus 3 to minus 4 to 13. And because that's a proportion, we can, if we choose, multiply by, say, minus 1, just to make it a little bit simpler, in which case it becomes 3 to 4 to minus 13. And then the equation of the line must be again, round brackets alerting us to the fact that we have a vector here. So this is our definition of what vectors are. And naturally enough, we could extend this, and eventually we will, to higher dimensional vectors, to 3-dimensional vectors, and so on. But to start off with, we'll just think about these 1-dimensional and 2-dimensional vectors, defined in this very concrete, explicit way. Now, still staying in the 1-dimensional situation, how do we introduce these displacement vectors in the context of points on an affine line? Well, if A and B are points, and say A is the point consisting of the number little a, and B is the point consisting of the number little b, then the displacement vector V equals AB. Okay, we define the displacement vector AB is this thing right here. It's a vector whose single number inside is B minus A. We take the coordinate of B, we subtract the coordinate of A, and that is what we put inside here. It's just a single rational number. So that's how we go from a pair of points to a vector. We just take the difference of the entries. But remember that we're starting from A and going to B, so what's inside here is the final entry minus the initial entry. Okay, it's the final entry minus the initial. So, for example, here's a line. Here's a couple of points. There's A, which is the point minus 3. There's B, which is the point minus 1. C is, well, a point with rational coordinates, say 2/3, between 0 and 1. D is the point 2. And E here is the point, say, 8/3, between 2 and 3. Okay, so let's have a look at some vectors. How about the vector between A and B, the displacement vector between A and B? So we write it as AB with an arrow on top, meaning we're starting at A and we're finishing at B. And how do we write that thing down? Well, it's going to have round brackets, and what's inside the round bracket has to be the difference between the B coordinate and the A coordinate. Okay, the B coordinate is minus 1. The A coordinate is minus 3. So if we take minus 1 minus 3, we get 2. So that's what sits inside here, that's 2. That corresponds with our intuition. Geometrically, we can see that going from here to here, we have to go over 2. 2 in the positive direction because we're moving right. And this is a positive direction in the x-axis. Now have a look at CE, the displacement vector between those two. There's C, there's E. To get the vector here, we have to take the difference. We have to take 8/3 minus 2/3. Well, that's 6/3, or 2. So the vector CE is also equal to the vector 2. So this displacement vector equals this displacement vector, even though they are in different positions. We'd have to translate this one to get that one, but they're actually the same vectors. And what about, say, the vector U, which is DB? Okay, starting with D and then going to B. Well, what we have to do is we have to take the final entry, which is B, which is minus 1, and subtract the initial entry, which is that D, which is 2. So minus 1 minus 2 gives us minus 3 inside. So the vector DB is the vector with single component minus 3, representing the fact that this is going to the left on our oriented axis. So vectors can have positive entries, can have negative entries, could also have zero entry. If it had zero entry, then it wouldn't be going anywhere. That would be a vector like CC, starting at C, ending at C. That would be the zero vector. It would be represented by round brackets with a 0 inside. So relatively simple vectors along the one-dimensional line representing displacements between points, and obtained by just taking the difference between the coordinates of the points involved. Final minus initial. Okay, so now let's look at two-dimensional displacement vectors. So suppose that we have 2 points in the plane, A, which is, say, AB, and B, which is CD. So these are affine points. And then the displacement vector, V, written as AB, the vector AB, is defined in the following way. This is how we define the vector AB. It's the vector whose components are C minus A and D minus B. So the difference between the x-coordinates, the difference between the y-coordinates. That's the definition of a displacement vector. And it is a vector because it's in round brackets and it's got a pair of entries. So, for example, if we have a couple of points in the plane, say A is 1, 1, B is 4, 2, C is minus 1, 2, D is 2, 3, then the vector V, which is the vector AB, How do we get that? We just look here. We look at the difference between the x-coordinates, so 4 minus 1, and the difference between the y-coordinates, 2 minus 1, we get 3, 1. And that's the same as the displacement vector CD, because if we compute that, difference between the x-coordinates is 2 minus 1, that's 3, and 3 minus 2 is also 1. So this vector AB is the vector V. You put a V there. And that's also equal to CD. They're both equal to V. So let's actually write that down. So we can give that the name V. And this is also the vector V. So vectors in a plane can manifest themselves in lots of different ways. Basically, we can take a vector like this and translate it wherever we want. As long as we don't move its orientation or change its extent, it's going to be the same vector. And here's another one. U is, say, AC. That's going from here to here. Let's give that a name. There's vector U. Then, how do we calculate that? So it's going from A to C, so we take the C point and the A point, take the difference. Minus 1 minus 1 is minus 2, and 2 minus 1 is 1. So the vector AC is minus 2, 1. And notice that this is just very natural. Going from A to B, you have to go over 3 in the x direction and up 1 in the y direction. So that's the vector 3, 1. To go from A to C, you have to go backwards in the x direction by 2. In other words, you have to go minus 2, and then you have to go 1 up in the y direction. So these displacement vectors really are measuring the separation between 2 points, telling us how far we have to go in either coordinate directions to get from one point to another. A fascinating aspect of vectors is that they naturally have an arithmetical structure. This is something that points don't have. Points don't have arithmetical structure particularly, but vectors do. Somehow being differences of things makes it easier to combine them. So in the one-dimensional case, here is how that arithmetic begins. It begins by defining the sum, the difference of vectors, and also a multiple of a vector. So here in the one-dimensional case, we have two vectors, A and B, and to add them, the definition is we just take the vector A plus B. Here we have the difference, A minus B is the vector A minus B. And here what we're doing is we're multiplying the vector A by some number lambda. So lambda is just some arbitrary number, meaning rational number. And so lambda times that vector is by definition the vector lambda times A. Correspondingly, in the two-dimensional case, it's very similar. We can define the sum of two vectors, the difference of two vectors, and a multiple of a vector in an obvious way. So to take the sum, we just take the sum of the x-coordinates and the sum of the y-coordinates. To take the difference, we take the difference in the x-coordinates and the difference in the y-coordinates. And to multiply the vector by lambda, we just multiply each of the entries by lambda. So these operations, this is what's called addition, or perhaps vector addition. Here's subtraction, or vector subtraction. And here's scalar multiplication, to remind us that we're multiplying a vector by a scalar, or number. So note that multiplication of vectors is not defined. We do not define the product of two vectors. Later on, one does, but not in perhaps an obvious way. So these are arithmetically defined operations, but of course they do have a geometrical meaning. Otherwise, they'd be rather pointless. Very important geometrical meaning. The geometrical significance of vector addition and vector subtraction is illustrated in this example. Here we have the vector u equals minus 1, 3, going from there to there, and the vector v equals 4, 2, going from here to here. Notice that we've arranged that these two vectors are not just anywhere, but that they happen to be both emanating from the origin. What's actually really important is that they're both emanating from the same place. That makes describing their sum and their difference much simpler. Remember that the vector, say v, vector 4, 2, can be translated in still the vector 4, 2. So we can go from here to here. That would still be the vector 4, 2. We translate it in many number of places. So if we put it right here, that's a particularly convenient spot because it's emanating from the origin. In that case, we see here in this diagram a parallelogram. Okay, so here there's a vector v, and here's the vector u, and the other sides are parallel to these sides. Parallel. So again, we're using this parallelism, which we're assuming that we have around in this affine geometry, to create this parallelogram. So this is actually a copy of the vector v, and this is actually a copy of the vector u. This vector and this vector are exactly the same. So when we look at u plus v, what we're doing is we're adding the x-coordinates to get 3, we're adding the y-coordinates to get 5. We get the vector 3, 5. Where is this on our diagram? Well, 3 over this direction, 5 up. It's the vector going from here to here. So this green vector is the vector u plus v. There it is right there. So that's a nice geometrical significance to the sum of two vectors. It's the vector that goes along the diagonal of the parallelogram that's spanned by u and v. And another way of thinking about that is it's what you get when you take v, and then you combine it with u. So you go along here in the direction of v, and then starting here, you go along the parallel translate of u from here to here. So the combination is to go from here to here. Right, so I'd like to now put some of these vector ideas to work in a very important kind of example to illustrate a physical principle that's naturally expressed with vectors. This has to do with moments and the centers of mass. And it really goes back to Archimedes and this famous law that he discovered called Archimedes' law of the lever, which tells us when two masses on a lever balance. Okay, so here's a lever, and we have some point there like this, and we have some masses, one on this side, one on this side, and we're interested in the situation when the thing actually balances, doesn't fall over. Okay, he noted that the relationship that's required for balance is a very precise one in terms of the two masses, let's call them M1 and M2, as well as the two distances, D1 and D2, from the fulcrum, the place where everything is trying to balance, to the bottoms of the masses. Okay, so that's D1 there, that's D2 there, and this is his crucial relation. That the lever will balance precisely when M1 times D1 equals M2 times D2. When the product of this mass times that distance equals the product of this mass times this distance. Now this has the effect that, let's say we do have a situation of balancing, and suppose that the mass M1 is, say, doubled. Okay, suppose you have twice as much mass there. So that one of these sides of this equation will be doubled. Okay, so suppose that we want to still keep things balanced. That means we have to double somehow this side here. So one way to do that would be just to double the mass M2. But suppose that you're on a seesaw and there's only you there, and so somehow you have to adjust to the fact that there's now two people sitting on the other side as opposed to just one. So what you could do is you could multiply D2 by 2. If you move out to double this distance, then this quantity, this total vector called the moment, will be still the same as this one on this side, and so you will still balance. Okay, so the point is that if you can compensate by increasing the mass by, say, decreasing the distance, or vice versa. So it's a very powerful relation, and really is responsible for all kinds of wonderful things in physics. Now we're going to look at this 2,300-year-old relation from a very modern point of view using vectors. It turns out that the language of vectors is ideally suited to not just reframe this, but actually to allow a broad extension of this principle. So the key idea is to think about something called the moment of a mass around a point. So let's call this point F for fulcrum. And we have these two masses, M1 and M2. And now let's think not in terms of distances, but rather in terms of displacements or vectors. Okay, so here we have a vector V1. This is the displacement from this point to the point right under the mass M1. That's the vector V1. And V2 on the other side is the vector, which is the displacement from F to the point underneath M2. So if we multiply a mass times a vector, we get another kind of vector object, which is called a moment. It's a different kind of vector. It's not really a displacement vector anymore because the displacement has been multiplied. We've expanded the vector, or perhaps contracted it, by multiplying it by the mass. So the mass times the vector is a new vector called the moment of the mass around F. Now in terms of these moments, the balance occurs when this relation is satisfied. When M1 times V1 plus M2 times V2 equals the zero vector. This is a rewrite of this original equation in the language of vectors. And you can see that we've exploited the fact that vectors have direction, because over here the distances are necessarily positive. But over here with these vectors, vectors can be positive if they're in that direction, and they'll be negative if they're in that direction. So that allows us to replace this equation with this equation where everything is on the left-hand side. M1 V1 plus M2 V2 equals 0. That's the condition that we require for balance. This is a very powerful way of writing this. It's actually a much better way of thinking about the balance condition or Archimedes' law of the lever. So let's give an example. Suppose that we're in the one-dimensional situation. We have three masses now. And we know exactly where the masses are. So there's a mass of 10 at the point, whose coordinate is -1. There's a mass of 3 at the point 1, and there's a mass of 5 at the point 4. So we're receiving masses of 10, 3, and 5 at -1,